For the first part of 4.4, our objective is to use the fundamental theorem of calculus to evaluate definite integrals. Let's start with derivative. What is derivative? What does it mean? Remember that derivative is another way to say the slope of the tangent line. So thinking of a graph, I'll give you a little example to look at. We can sketch something. We'll call this y equals f of x. And I'm going to pick a point somewhere on here, and I'm going to say to find the derivative of this, what I mean I'm finding is the slope of the line that's tangent at this point. So normally, to find slope, I need to have 2 points and do the change in y divided by the change in x. But to find the derivative, that's dy dx. That's the exact slope at that point. Let's take a moment and talk about what is area. Lately, we've been talking about area. Let's just look at a graph. And I'm going to try to draw a similar function to what I drew on the left. And again, I'm going to call this y equals f of x. And I'm going to mark off from one x value, we'll call it a, to another x value b. And when we've been talking about area, we've been saying the area between the function and the x-axis from some x value to another x value. So I'm going to shade in that area so we can get an idea for what we're talking about. And we've said, well, we can't find that exact area. Of course, we've, used a limit process, but we started the limit process by saying, let's estimate a rectangle that does a little bit of underestimating and a little bit of overestimating, and we can find the area of this rectangle. Well, how do we find the area of this rectangle? Well, we do the width times the length, or times the height. What's the height of it? That's the change from this y-coordinate to this y-coordinate, so that's the change in y. And what's the width of it? Well, that's from this x-coordinate to this x-coordinate, so that's the change in x. So area, this area that we're looking at here, is approximately the change in x times the change in y, its length times its height. So notice these two scenarios side by side. We've done a lot with derivatives, the slope of the tangent line, and it looks like dy over dx, or the change in y over the change in x, versus when we did area, which is the change in y times the change in x. Notice how they are inverse processes of each other. In the slope, we are dividing change in y and change in x, and in area, we are multiplying change in y and change in x. Dividing and multiplying are inverse processes. So what else does this tell us? That tells us that the derivative and well, what's the inverse process of the derivative? That's right, the antiderivative. So whereas slope is the derivative, the inverse process of it is the antiderivative. So now we start to make some connections. If you remember in the previous section, we started talking about definite integrals. Well, a definite integral comes from an integral, and remember the synonym for antiderivative was indefinite integral, so that was that integral symbol, the integral of some function with respect to x perhaps. Well, the definite integral is when we just put those limits in there. So the derivative, or the slope, change in y divided by change in x, is the inverse process of the antiderivative, or the area, change in y times change in x. So now we see that the antiderivative is helping us to find the definite integral. And this is basically the fundamental theorem of calculus. Now in your notes, We're saying f is a continuous function. Remember, if we're creating area, we need a continuous function on an interval. Capital F will represent our antiderivative of little f on an interval a to b. Then the definite integral from a to b of f of x dx is the antiderivative evaluated at the upper limit minus the antiderivative evaluated at the lower limit. So this is our shortcut so that we don't have to use that big limit process for the definite integral. Now we know that the antiderivative is the inverse process of the derivative. Therefore, because area is the inverse process of the slope, area being the inverse process of the slope, we know we can just use antiderivatives to find the definite integrals. So let's use this shortcut process for our definite integrals. Evaluate the following integrals using the fundamental theorem of calculus. That means the shortcut. We don't have to go through the limit definition anymore. So let's start with thinking about what the integral, the antiderivative, means. We look at our function x cubed and we do our power rule. Add 1 to the exponent, that makes x to the 4th, divide by the new exponent. And here's the symbols that you're going to use. We've done the antiderivative, so we don't put the integral symbol anymore. Now we're going to put a bracket here to say we still need to evaluate from 1 to 2, so let's not forget to do that. We're going to plug in the upper limit, plug in the lower limit, and subtract them. Let's look back at our definition of the definite integral, as the fundamental theorem of calculus, f of x dx. That's the antiderivative at b minus the antiderivative at a. That's what you wrote down above. So b is our upper limit, a is our lower limit. So we have this. We're going to plug the 2 in, plug the 1 in, and you see that we're subtracting them. So we get 4 minus a 4th, or 3 3/4. Now you might have been wondering, why aren't we writing plus c? Well, let's look at it if we had written plus c. X to the 4th over 4 plus c, evaluated from 1 to 2. Of course, we never want to forget plus c when we're doing antiderivatives. But I plug in 2 to the 4th over 4. This is plus c. I subtract 1 to the 4th over 4 plus c. Well, what happens when I combine like terms? The c's subtract away. So I still end up with 3 3/4, but the c's canceled out, and I don't have to write the c if I know that it's going to cancel out. So I tend not to write the c, and you tend to see the c not written in definite integrals. Let's look at another one, but look closely at this. Do you see how it's almost identical to the first one? Almost. The function is the same. The integrand is the same. But what's different? The limits have been reversed. So we don't have to go through the whole process of evaluating this by using the antiderivative. We know this is just the negative of the integral from 1 to 2 of x cubed dx. Do we normally switch it if it looks like the numbers are backwards? No, but I'm switching it because we already found the definite integral when the limits were reversed. So we know this is the same as the previous answer, just the negative of the previous answer. So think about some shortcuts you can use because we need to save time for the ones that really give us trouble thinking. Here's another one with part of the same function. We have x cubed in there, but our limits are different. Now we're going -1 to 1. Well, when I first see these, I think to myself, equidistant from the origin, meaning graphically -1 and 1 are the same amount of units away from the origin. Well, why am I thinking about that? Because x cubed by itself is an odd function. X squared is not, but what that means is if I split up this integral, -1 to 1 of x cubed dx plus -1 to 1 of x squared dx, we know that because this one is odd, meaning looks like this, we get the same amount of area above and below the x-axis. Since definite integral means the net area, we know that this is just 0. So we really only have to evaluate this one. So we can go ahead and do this by doing the antiderivative. X squared is x cubed over 3. Evaluate from -1 to 1. plug in 1 cubed over 3 minus, plug in -1 cubed over 3, and in the end, 2/3. Now, another thing I want you to think of is when we have an even function, because part of this is an even function, the x squared, this one, the one we evaluated, this is even. What does that mean to us? That means we can do a little shortcut here. Let's take some room to look at this. If I sketch out what y equals x squared looks like, between -1 and 1, the area here and the area here, exactly the same amount of area. What does that mean? My shortcut for this, perhaps a shortcut, is saying the integral from -1 to 1 of x squared dx is the same as saying the integral from 0 to 1 of x squared dx, this part on the right side of the y-axis, but doubled, because I have two of these, because I know about the symmetry of this. This is kind of nice because 0 is easy to plug in and get simpler values to work with than plugging in negative numbers. So this means I can do the antiderivative, evaluate from 0 to 1, multiply what I get times 2. Well, see, plugging in 0, that's just going to be 0, so I have 2, 1 cubed over 3 minus 0, or just 2 times a third, or 2/3. So just some things for you to think about. Can be some nice shortcuts. I want you to remember, and this is from an AP exam, what you do when you see a quotient. We don't have a quotient rule, but we cannot do the antiderivatives when it's a quotient. So remember that we rewrite a quotient or a product. We do not leave quotients and products and take antiderivatives of those pieces. So rewriting means divide the x cubed into both of those. X over x cubed minus 4 over x cubed. Still need to rewrite it. Keep putting that integral symbol, x to the -2 minus 4x to the -3. Now we're ready to do our antiderivatives. That one is x to the -1 over -1 minus, remember we're adding 1 to each exponent, 4x to the -2 over -2. Put our brackets, put our limits. We don't need a plus c because it's going to subtract away. Now we can rewrite our negative exponents. We don't want to leave negative exponents when we know we have to plug in values. So I'm going to rewrite this as -1 over x minus, this will become a plus, and 2 over x squared on the interval 1 to 2. Then we'll plug in our values. Top always goes first because we're subtracting. We want to do the big number usually minus the small number, but we always go with what's on top first. -1 over 2 plus 2 over 2 squared. Because I have multiple terms in this expression, I'm going to put parentheses, then say minus, and now plug in the 1. -1 over 1 plus 2 over 1 squared. Then I can simplify this. -1 is what it cleans up to. Again, from an AP exam, looking at things a little bit differently. How are we going to figure out what the k is when the k is in here? Well, let's do the parts that we can do. We know that we do the antiderivative of what's in here, so we can do x to the 6. Well, we don't know this constant. You know what? Let's look at this as a shortcut. I just noticed this one is odd. So if we split this up, -2 to 2 of x to the 7th, plus -2 to 2 of k, well, because this one is odd, we know that that's going to be 0 when the limits are equidistant from the origin. That's when we can say the odd function is going to have a net area of 0, equidistant from the origin. Then we can use our antiderivative, and it's a little bit faster. So being a constant, we know the antiderivative will be constant times x. Evaluate from -2 to 2, and remember they told us what it's supposed to equal, so let's continue to write that so we don't forget. Plug in our upper limit, k times 2, plug in our lower limit, -2, keep writing equals 16, and simplify this, 4k equals 16, so k equals 4. Go to the next video for the absolute value.